I'm Jarno Alanko, and this is Matchtigs, a minimum plain text representation of K-mer sets in collaboration with these people from the University of Helsinki. I'm working in the University of Helsinki and also part-time in Dalhousie University. So this talk is about spectrum preserving string sets. So in metagenomics, a genome is often seen as just a bag of K-mers, and this set is called the spectrum of the genome. And a spectrum preserving string set is another set of strings which has exactly the same spectrum as the original strings. So exactly the same set of K-mers. So for example, here if we have an input set of sequences ACTTG and CTTGC, and K is 4, the spectrum would have 3 K-mers shown here in the middle. And on the right, we have an example of the spectrum preserving string set ACTTGC. It contains all of the 3 K-mers of the input. And we abbreviate spectrum preserving string sets by SPSS. So examples of SPSSs include unitigs. So the unitigs of the de Bruijn graph are automatically an SPSS by definition. Then we have these 2 methods called UST-tigs and simply-tigs. So these are methods which take the unitigs and stitch them together to form longer strings. And this doesn't change the set of K-mers represented. So therefore, the spectrum is preserved. So these are also SPSSs, but they have a smaller size than the unitigs. But they are not optimal. So the question is then, what is the smallest possible SPSS for a set of strings? And this is an open problem, and it's been conjectured to be NP-hard, because it's very closely related to the problem of minimum path cover. But in this work, we show that it's not NP-hard. Actually, it is linear time computable, which is quite surprising. So the first step is to reformulate the problem. So we go into the language of graphs. So the minimum SPSS corresponds to the minimum path cover of your de Bruijn graph. And this is still an NP-hard problem. So minimum path cover is NP-hard in general graphs, but here we have a specific special case. So in de Bruijn graphs, you cannot have any shape. For example, you cannot have this subgraph in the graph. So if this was a node-centric de Bruijn graph, you would have to have an edge from the bottom left to the top right. Otherwise, it's not valid. So you see the topology is restricted, which allows us to have a polynomial time algorithm. So I'll now describe how we do this. So let's do a warm-up problem first. So let's solve a simpler problem, which I call the spectrum preserving string problem. So here I ask whether there exists one string which has exactly the same K-mers as the input. So not a set of strings, just one string. And now, unfortunately, this corresponds to the Hamiltonian path problem in the de Bruijn graph, which is also NP-hard. But here comes the trick. So there are 2 definitions for de Bruijn graphs. One is called node-centric and one is called edge-centric. So in the node-centric graph, the nodes are the K-mers and the edges are the overlaps. And in the edge-centric graph, it's the other way around. So whereas this problem is the same as the Hamiltonian path problem on a node-centric graph, if you look at the edge-centric graph, it's actually the Eulerian path problem. This is the problem where you need to cover all edges of the input using one path. And it's been known for at least a century that you can find an Eulerian path in linear time on an edge-centric, on any graph, but in particular on an edge-centric de Bruijn graph. So this gives us a linear time solution for the spectrum preserving string problem. And I'd like to highlight here how formalism matters. So it is the same problem, just phrased a little differently. And the problem goes from this intimidatingly hard Hamiltonian path problem to this Eulerian path problem, which is a very known problem and easy to solve. So now, let's go to the spectrum preserving string set problem, where we need to find the smallest set of paths to cover the deborahing graph. So surprisingly, this is not much harder than the previous problem. So the algorithm goes like this. We find the smallest number of edges we need to add to the graph to make it Eulerian, to make it have an Eulerian path. This is quite easy to do. Then we compute an Eulerian cycle, and then we delete the edges we added, breaking the cycle. And we can prove quite easily this is the smallest possible path covered for the graph. So let's do an example. Suppose this is our graph, and now we want to make it have an Eulerian cycle. So in here, I assume it's strongly connected to make it a little bit simpler. So here I've listed for each node the imbalance of the node. So the imbalance is defined by the number of incoming edges to a node minus the number of outgoing edges. So for example, this node here, if you can see, has 2 incoming edges and 1 outgoing. So 2 minus 1 is 1. It has imbalance 1. So positive imbalance means more incoming edges. Negative means more outgoing edges. So we want to make it so that every node has imbalance 0. If this is the case, then we can find an Eulerian cycle. So what we do is we add edges from the nodes with positive imbalance to the nodes with negative imbalance. So for example, we could add these edges. It doesn't matter which set of edges you add, but this is one. And now with this, we can find an Eulerian path. Any Eulerian path will do. And then you delete the edges you added, and you're left with these paths, and this is your solution. So this solves in linear time the minimum SPSS problem. Right, but it doesn't end there. We have another variant where what if the paths do not have to be disjoint? So here's a variant of the problem where you need to find the smallest set of strings which have exactly the same set of k-mers as the input, but you can have duplicate k-mers. So this is like a relaxation of the problem. So if you do this, you might find a smaller set of strings with a smaller total length. So for example, if you have this X shape in your graph, if you cannot repeat k-mers, you would need to use 3 strings. But if you can just reuse the middle k-mer. And even though you duplicate the k-mer, the total length of the strings ends up smaller. So this relaxation of the problem is also solvable in polynomial time. It is very related to a classic problem called the directed Chinese postman problem. We basically use the same methods as they do with a little changes. So this is reducible to minimum weight perfect matching. I won't explain the reduction here, but you can read the paper for that. So this solves the problem, but it's no longer linear time because minimum weight perfect matching, we don't know a linear time algorithm for it. The classic solution is cubic, and there's something like quadratic times some factor exists, but the worst case of this algorithm is quite bad. However, there exist solvers for this minimum weight perfect matching problem, which seem to work quite well in practice, at least in our inputs. And we also show that a simple greedy heuristic also performs quite well. So here's a sample of the results. So in this experiment, we have a data set of 3,682 E. coli genomes, and we're comparing the size of 6 different TIGs or SPSSs. So UniTIGs is your basic SPSS, and we normalize this table so that UniTIGs also are UniTIGs are always 1.0, and everything else is relative to the UniTIGs. So the total length of the UniTIGs is normalized to 1.0. So we see that these 2 methods, UST-TIGs and ProFASM, so these were the UniTIG stitching methods, they cut the total length from the UniTIGs by about 40%. And then we have Euler-TIGs. So this is the optimal solution to the problem that these 2 methods try to approximate. so without repeating k-mers. So we see that these stitching methods are already almost optimal, within 1%, at least this prophasm in this case. So, but this is the first time we were able to show this, because this problem, we didn't know how to solve this problem exactly before, but now we know they are very, very close to optimal. So then these last two tigs are called Matchtigs and G-Matchtigs, where G stands for greedy. So it is our linear time approximation. So we show that by repeating k-mers in your SPSS, you can reduce the total length of the unitigs by about 10%. So there are significant gains to be had there, at least in this data set. Now in the next column, we have string count. So this is the number of strings in your final solution. And here I'd like to just highlight that if you can allow repeats, then minimizing the total number of strings is no longer the same problem as minimizing the total length of the strings. And in this case, the greedy matchtigs actually give a lower number of total strings than the total length of the strings in the matchtig in the optimal solution. But if we also have a polynomial time algorithm to optimize the string count as well, but it's not shown here. Now for the time and memory, they are quite similar, with prophasm being much slower, but this is probably due to it not being very optimized. The algorithm is actually very simple, so I think this running time is more of an artifact of the implementation. Right, so that's the end of the talk. So our contributions is we have solved two problems. One is minimum SPSS without repeats, thought to be maybe NP hard, turned out not to be. And then this variant with k-mer repetitions, we can also solve in polynomial time. And in practice, we can use a matching solver to solve it fast in practice. We show that greedy heuristics are very good already, so you don't necessarily need the exact solution, at least in our data sets. So this has some applications. For example, the first thing is k-mer set compression. So the SPSS represents the k-mer set. The smaller the SPSS, the smaller representation you have. And then when you've compressed the k-mers, you can feed these to downstream applications such as Bifrost or SSH, which was just presented, which will benefit from having a smaller SPSS. So, and then there are some details I didn't talk about. And the biggest one is reverse complements. So actually, the way we usually define this is we define that a k-mer is equal to its reverse complement. And this makes things very complicated. Well, not conceptually. The same algorithms still work, but now the model, the graph model, becomes bidirected graphs to model these reverse complements. But it's more of a nuisance. You can still do it, but you need to be very, very careful with this. Reverse complements and palindromic strings in particular, but the core ideas are the same. Okay, thank you.
So I like this very much. Nice problem. So I was wondering, what if you allow superior k-mers, but you store the exceptions somewhere? Would it be possible to get like a small representation?
What do you mean by spurious?
The ones that are not in the original. So you sort of have a string that is some k-mers that are not in the original string, but then you store them separately and exceptions. So you check.
Ah, okay.
Would it be possible to get a small representation?
Yeah, possibly. Yeah, it's not in our model, but maybe. Thank you.
Hi, interesting work. So have you ever thought about generalize your algorithm back to the minimum power problem? For example, under which condition the minimum power problem can be solved in polynomial time or even in linear time?
Yeah, so there is some work in the math literature. There are a family of graphs called adjoint graphs. We found out about this after our work. So some mathematicians have shown that the minimum path cover is NP hard, not NP hard, it's solvable in polynomial time in adjoint graphs. And the Deborah graphs are a special case of that. So actually this problem, which was thought hard, it was already solved in the math literature, but the people didn't talk to each other. So that solution was not known. But there's still one complication, which is this bidirected graph. So they didn't do it in the bidirected case, whereas we do it there. So you couldn't just directly apply their results if you want to consider reverse complements.